Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. It's really great being a scientist. I love being a scientist. I love studying weird, funny things happening inside the universe. And I love chatting to everybody about all of the cool things I get to study. So for anyone who's unfamiliar with Cup of Cosmology, this is an interactive stream. The idea here is that you people can ask me anything you want about cosmology, about space, about physics in general, about time even, if you want. Those are always fun questions. About academia, about me, ask me anything means literally you can ask me anything. I might not always answer, but you are welcome to ask anything. To any first-time viewers, welcome. Hope you enjoy it. To all the regulars tuning in, as always, thank you. It's so nice to see all of you coming back. I see we have Ben, we have Ange, we have David Howden. Great to see you all here. Great, David Dunn, the other David in as well. We have 3 or 4 Davids who join regularly by now. Great to see some of you coming in. If you haven't done so yet, please do like the video, leave a comment, say hi, tell me where you're coming from, tell me what you're doing, or why, just say hi, check in. You're also welcome to lurk, but this is an interactive stream, so the more you interact, the more fun the stream is. So do feel free to jump in the comments, even if it's just to say hi, even if you don't have questions, but you are also welcome to just watch quietly. I am indeed not in fancy dress in the end. Yes, I did say last week that I might not do a stream today because there is a costume party happening downtown at one of my favorite hangouts, Western themed. I was very much planning on going, or at least thinking of going, and I've just had a ridiculously busy and slightly overwhelming week, and I was out yesterday, and I just cannot manage yet another thing today. So I decided I do not have social energy for a costume party, but I do have energy for Cup of Cosmology. So I also toyed with the idea of just putting on a Western costume for Cup of Cosmology, Cup of the Wild West, but let's keep this show semi-serious. This show is not serious, but let's just keep it semi-serious. So I make a lot of jokes about having a lot of Davids in the chat here, because there is a joke that goes round in academic circles that sometimes you go to conferences and there are more people there named David than there are women. And I have been at such conferences where there's more men with a shared name than there are women at the conference. And it's kind of like an ongoing joke that sometimes that happens. It's not something that should happen. It's not something that is a nice situation to be in, but it's the ongoing joke. And I think it's funny that we have 3 or 4 Davids who tune in regularly, because it reminds me of that. So that's why I frequently make the comments. But yes, petitions for all of you to change your name to David, then it's easier. Go for it. Yes, I see that's not what you wrote, but close enough. Go for it. Yeah, I should have come to Cup of Cosmology in costume. I feel like that then the show would take a very different direction. Could also be very fun. I should do that one evening. Like one weekend, just like whatever. There's a Cup of Cosmology, full-on costume. I do still want to do the steampunk one that was discussed a couple of years ago with a friend, just like Cup of Cosmology steampunk edition. That would also be cool, because science is something that should be fun and enjoyable, and we should mess about with it, and it is not a serious thing. So yes, I'm all for doing weird things with Cup of Cosmology, and I will look at doing like themed episodes in the future and wear outfits to match. I realized that, so I'm currently at a conference remotely. Obviously, as you might recognize, this is my usual background. I am indeed at home, but I am participating in a remote conference called Neutrinos from Home, which is all about neutrinos, and as the name implies, it's from home. It's a fully remote conference. I love the idea of remote conferences. I think all conferences should be hybrid. I love the idea of remote conferences. And I was going somewhere with this, and I've completely lost the point of why I was mentioning this. But anyway, I'm attending this remote conference, and it is a very, very fun conference. And yeah, there was a point to me saying that. What was the point to me saying that? There was a point somewhere. There was a point. It ran away from me. It happens sometimes. Anyway, I'm currently attending this remote conference called Neutrinos from Home. It is a very, very fun conference, and there's a lot of exchange of information, and it's really, really nice to be at such events that are happening entirely remotely, because it's just really nice to be able to do this from the comfort of my own home. As someone who is chronically ill, having the option of attending conferences remotely is extremely appreciated. So yeah, I am currently attending a remote conference called Neutrinos from Home, which is all about neutrinos. And this was the inspiration to do a whole stream on the topic of neutrinos. So today we actually do have a topic. The topic for this week is going to be neutrinos and cosmology. So basically, what are neutrinos? Why do we care about them? And I'm going to draw on stuff that we've talked about in week 1 of the conference. There is still a second week of the conference to come. Also, I'm pretty sure by now that there is going to be a live stream for the conference. Like, the conference organizers are planning on setting up a live stream. I have volunteered because of course I have. So I might be on that. If that is happening, I will give you information. I was hoping to be able to announce it today, but I still don't know when this is happening or if it's happening. As soon as I get information about the Neutrinos from Home outreach event, I will let you all know, because I feel like it will be closely related to what we're discussing today. So you will also all be very welcome to watch that and ask questions there, because that's the point of these things. We always need more questions. Hey, Scott, great to see you. You do indeed have photos of me in a Stetson. Yes, there are photos of me in a Stetson. I believe when I graduated my bachelor's, master's, one of those, when I graduated at some point, I was kind of not really keen. So the university, for some reason, didn't do the big celebration with the hats. So instead, we improvised the celebration at home with my family, and I put on a Stetson because it was the first hat we found. And I artistically threw the Stetson hat, pretending it was my graduation cap. And there are photos and I believe videos of that. It's very funny. The world direly needs more cowboy astronomer representation. I agree. I very much agree there. I think we do need more fancy dress, more whimsy, more fun in physics and science. Science is fun, and it should be fun. Cowboy, cowgirl, cowperson, cowboy. Yeah, I feel like, to me, cowboy feels gender neutral, although it isn't. But to me, cowboy feels gender neutral. You need more neutrinos at home. Well, the good news is there are billions of neutrinos in your home right now. Don't speak too loudly. They're listening. Don't worry, neutrinos are not a problem. They're not interacting. They're not going to do anything. But there are neutrinos, and we're going to get into that in more detail once I've stopped rambling. I'm still trying to remember the point I was about to make, because I started saying that I'm attending a conference this week, and there was a point to that. But that point has escaped me. So I'll watch back the replay later and be like, oh, that's where I was going with that conversation, right? It happens. Brain is sometimes a bit scattered, and I did not get enough sleep last night, so brain is very scattered today. So this is probably going to be even more hyperactive than usual. Yes, it was indeed after my undergrad, when I finished my undergrad, that we did the Stetson hat celebration. I should re-find photos of that. That was a fun event. Okay, rambly introduction over. Let's get down to business, as Mulan song says. Whew, this is going to be a fun one. Okay. Also, if you wonder why I keep looking distracted, it's because my new plant suddenly looks very droopy, and it is a new plant. It should not look droopy. That is a problem for after the stream. Okay, so today I want to talk to you about neutrinos. And neutrinos are a really fun topic, and one of the reasons that I think neutrinos are really, really interesting is because it's something that lies at a lot of the overlap of a lot of different fields. Neutrinos are relevant for cosmology, they're relevant for particle physics, they're relevant for astrophysics. So it really does bring together a lot of different fields and a lot of different people. And this is something we're seeing at the Neutrinos from Home conference that I'm attending, where we have people from vastly different disciplines coming together. And it's really nice because then we get to discuss different points of view. So at this conference, I gave the introductory overview talk of how we study neutrinos from cosmology, which was honestly pretty terrifying to do. And I've just remembered the point I wanted to make. So this talk was a bit intimidating and scary to do, because there's about 120 participants at the conference. And I feel like there are people who have worked on neutrinos a lot more than me, but I was there to give the neutrinos overview introduction talk, which is a bit scary. And the reason I'm mentioning this is because I think it's important to talk about the fact that imposter syndrome is something we all deal with, regardless of career stage, regardless of how someone might appear from the outside. Imposter syndrome is something that pretty much all of us deal with. I'm getting asked to give one of the pedagogical overview talks at a conference always fills me with a sense of, oh God, why did they ask me? I'm not qualified to do this. But turns out, I am qualified. I did the talk. It went really well. I got good feedback on it. So guess what? I am qualified, no matter what my brain tells me. And I think it's important to remember that that's a feeling that we all have sometimes. Things are scary, but we do them scared anyway, and we usually do a good job, because if someone's asked us to do it, it's not because we trick someone, it's because we actually know what we're doing. And it's important to remember that sometimes. Now, the point I was going to make randomly, we were talking about costumes and coming to Cup of Cosmology in a themed costume. So at the Neutrinos from Home conference, I designed my slides. I always put way too much attention into my the color scheme of my slides. And I realized that for the talk of Neutrinos from Home, I'd actually color coded my shirt to match my slides. So it looked like I was just like part of the presentation. And that was very cool. So I'm definitely going to do that again. And that was the point I wanted to make about why I suddenly jumped into conference when we were talking about costumes. But the conference is relevant to today. So, hey, Nadia, great to see you as well. I see we already have the first question about, can human bodies spontaneously emit neutrinos? I will get to that. I'm just making a note of that because I don't expect my brain to remember questions today. It seems like my brain is a tad scattered. Okay, so mentioned the word neutrinos quite a few times. So let's jump into it. What are neutrinos? So the universe, as we know, is made up of three components. Everything we see, everything we're accustomed to, everything from me to the stars you see in the night sky, to my tea mug, to my pen, to the cowboy costume that is somewhere in this apartment. All of this is normal matter. And normal matter is only 5% of the energy budget of the observable universe. There's another 26% in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally but does not interact electromagnetically. So dark matter is essentially invisible. And then the remaining 69% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that is pretty much everything we know about dark energy. So usually I do this introduction and then I jump into either dark energy or dark matter, but today I want to focus on normal matter, although later I'll mention that neutrinos may actually be more connected to dark matter than you think. So today we're going to focus on normal matter. If you're at a conference dressed as a neutrino, you cannot interact with the other attendees. Exactly, that's a problem. If you dress up as a neutrino and you want to go for realism and stay in character, you won't really enjoy the conference. Why? Because neutrinos don't interact. So let's jump into what are neutrinos. Focusing on the 5% of normal matter in the observable universe. This 5% of normal matter is made up of 17 building blocks. These are divided into fermions, which are the 12 you see on the left, and bosons, which are the ones on the right. The fermions are the building blocks of normal matter, and the bosons tell these building blocks how they can fit together. So any particle that you can think of is made up of fermions, but the way these particles interact, this is determined by the bosons. Within the fermions, we have two families. We have quarks and we have leptons. Quarks are ones that cannot be found alone. You never find one up or one down. You have all of them together. Not all of them together, sorry, but you cannot find one up. You always find an up with two downs or a down with two ups. You don't just find that here's a quark. Quarks are always bound together with other quarks. Leptons, on the other hand, can be free, can do their own thing. Now, within the fermions, so the quarks and leptons, we usually talk about three families, and this is just about the different masses. So the lightest family is like the leftmost one, then the middle mass, then the highest mass, although, caveat, this might not be the case for neutrinos. So you have the first family, the second family, the third family. When we're talking about the leptons, the ones can just roam free. The three families are usually the electron family, the muon family, and the tau family. And then at the bottom row, we have the leptons. Sorry, at the bottom row, we have the neutrinos. And neutrinos are what I want to talk about today. So neutrinos are this bottom row of the standard model of particle physics. They are the lightest particle within this block that actually has mass. We have some that have no mass, like the photon and the gluon, which are bosons. Photon is responsible for electromagnetic force. Gluon is responsible for strong force, so for gluing things together. These have no mass. But if we look at the mass, which is the top leftmost number in all of these little boxes, there's a number top left, you can see all of them either have mass or have zero mass. And then we have the neutrinos at the bottom, where we just have things like the mass is smaller than 2.2 something. The mass is smaller than, but we don't actually know the mass of these particles. So neutrinos are tiny, tiny subatomic particles that are part of the standard model. And they are interesting for several reasons. Now, number one, Neutrinos do not have any charge. This means that neutrinos do not interact via the electromagnetic force. Neutrinos are neutral. The name neutrino actually means the little neutral one. It's a neutral particle that is smaller than the neutron, which is also the neutral one. So neutrinos are these tiny particles that have no charge. If they have no charge, they do not interact via the electromagnetic force. So this means that it's very hard to see neutrinos because they don't emit light, they don't absorb light. As far as light is concerned, neutrinos are not there. But neutrinos do interact via the gravitational force, and they do interact via the weak force. So there are four forces that govern the universe: electromagnetic, which is electricity and magnetism; gravity, I drop pen falls down, we stay in orbit around the sun. We have the weak force, which is responsible for any type of particle decay, and we have the strong force, which glues things together. So neutrinos do not feel the electromagnetic force, but they do feel the weak force, and they do feel the gravitational force. So this means that neutrinos are extremely difficult to see. Then there's also the thing that neutrinos have very, very, very small mass, but they do still have mass. Because they have a slight mass, they can't travel completely at the speed of light, but they almost travel at the speed of light. So neutrinos are these tiny particles that zip through the universe pretty much undetected. If you hold up your thumb and look at your fingernail, every second, a couple hundred of neutrinos just pass through the tip of your finger. So every second, I have a couple hundred of neutrinos just going through. But because they don't interact electromagnetically, you're not going to feel them in any way. They're just doing their own thing. Now, when neutrinos were first discovered, people thought neutrinos did not have mass. They did not have mass, and they traveled at the speed of light. This was our idea of neutrinos. However, going back to the idea here of three types of neutrinos, where you have the electron neutrino, the muon neutrino, and the tau neutrino, people managed to come up with ideas of how to measure neutrinos. So neutrinos themselves are very difficult to measure, but neutrinos do carry away energy. So if you have a particle interaction and you produce neutrinos as a byproduct, these neutrinos are going to carry away mass. And one of the things we're pretty sure about in physics in general is conservation of energy. The energy you put into something is the energy that comes out of something in some form. Energy can be transformed, but it cannot be destroyed. So if you smash particles together or you have a particle decay, the initial energy and the final energy should be the same. However, if it's not the same, then you can say, okay, there is missing energy, and this energy is probably carried off by a neutrino. This is what gives people the idea to kind of look for neutrinos. Now, neutrinos can be produced by many, many different things. For example, in the sun, you have constant nuclear reactions happening. These nuclear reactions are going to produce neutrinos. In exploding stars like supernova, stars that have reached the end of their lifetime and collapsed, there you're also going to produce neutrinos because you have a lot of nuclear reactions happening. You can also produce neutrinos in a lab by just mimicking these nuclear reactions. And then the ones that I'm personally very interested in are the neutrinos that were produced in the first fraction of a second of the universe, the early universe neutrinos. We'll come back to those later. So if you have the idea, okay, the sun is going to produce neutrinos, based on everything we know about nuclear physics, we can predict how many neutrinos the sun should produce every second. And then you can set up a detector where you try to look for neutrinos coming from the sun. Now, of course, you're not going to be able to measure these neutrinos directly, but you can try to get neutrinos to decay inside your detector into something else. For an example, into a muon or into an electron, and then you measure that. So you can point a neutrino detector at the sun and measure all of the neutrinos coming in. Now, when people did this initially, they found about a third of the amount of neutrinos that they expected. I am seeing all of the questions. I'm going to come back to that in a minute. Just a note that I want to get through what I'm going to say first, and then I'm going to go to questions. I'm going to jump back and forth. But for now, I will get to your questions. Keep them coming. Don't worry. I am not ignoring you. I will answer your questions soon. So when people measured, back in the 1960s, people measured the amount of neutrinos coming from the sun, and they found about a third of between 1/3 and half the amount they expected. So there were a lot of neutrinos missing. This is something that was known as the solar neutrino problem. Where are the missing neutrinos? People double-checked the experiment. People double-checked the physics of like, okay, have we actually understood nuclear physics? Do we know what is happening in the sun? And eventually people realized that the reason we only see like 1/3 of these neutrinos is because the neutrinos are changing flavor. So if I go back to my standard model here, we have electron neutrino, muon neutrino, tau neutrino. But the neutrino doesn't decay into something heavier. It can have a weak interaction with something that then has a muon coming out. So for an example, if you have, you can have a muon neutrino bump into a muon, and this would produce an electron as a byproduct. So it's this reaction here. It's not really the electron decaying, it's the electron bumping into something via a weak interaction and then producing a particle that you can actually measure. So you look for the byproducts of the weak interactions of the neutrinos with other species, not neutrino decay, because particles can't decay into something heavier. It's really the weak interactions with neutrinos and something else that will then produce a byproduct that you can actually measure. So we have electron neutrino, muon neutrino, tau neutrino. The very cool thing that people discovered is that neutrinos can actually change between these. The other particles don't. An electron is an electron, a muon is a muon, a tau is a tau. The neutrinos, however, you can produce an electron neutrino in the sun, and by the time it reaches you, it might be a muon neutrino, it might be a tau neutrino. And these jump back and forth. It can go from electron neutrino to tau, to muon, to tau, back to electron. It can do this in any direction. This is really, really cool. This is the only particle we know of that can change between these different flavors. So this is something that explained the solar neutrino problem, because the detector that was measuring the neutrinos coming from the sun was set specifically to measure electron neutrinos, and it was getting about 1/3 because it was not finding the muon neutrinos and the tau neutrinos. Once this was realized and the experiment was changed to detect all possible neutrinos, they actually got the right amount, the amount they predicted. So neutrinos change flavor. Neutrinos can be produced as a muon neutrino, but by the time they reach Earth, they might be an electron neutrino, a tau neutrino, or they might still be a muon neutrino. The fact that they're able to change flavor means that they have to have mass, because there is a connection between the flavors and the mass. And it is not as simple as saying, like, okay, the electron neutrino has this mass, the muon neutrino has this mass. There are 3 possible masses for the neutrinos, there are 3 possible neutrino flavors, and these are entangled. So you can't cleanly pull out, like, here's a neutrino, an electron neutrino, it has this mass. And this is why we don't know the neutrino masses. We know they have to have mass, because if they didn't have mass, they wouldn't be able to do this flavor changing. So we know neutrinos have mass. We do not know how massive they are. Okay, recap. Let's just recap. Then I'm going to go to questions. Neutrinos are particles that are part of the standard model of particle physics. They travel extremely quickly, almost at the speed of light. They have tiny, tiny, tiny mass, but we don't know what this mass is. And neutrinos have the cool thing that they can change from one flavor to another. So there are 3 flavors of neutrinos, and neutrinos can change back and forth. The flavor and the mass are kind of connected, but not in a direct way. So it is very difficult to figure out the masses of the individual neutrinos. Neutrinos are also extremely difficult to measure because they don't interact electromagnetically. So that's just a quick recap of what I said so far. Now let's jump into questions, and I'm just going to start with this comment here by Nadia, because I see it mentions Wild West. So probably not a question. And Angela Collier said there were notable scientists denying the existence of atoms at the time of the Wild West. Neutrinos might be tough to shoehorn into the era for a costume. Yeah, I feel like neutrinos would not be a Wild West theme. So excellent question here. I'll just, before I go to the ones there, why do we call it flavor? Because we were out of ideas, basically. There is no reason to call this flavor. We call it the flavor of the neutrinos, but that makes no sense. It's not like an actual flavor. We also give different properties to particles. We call them, we say we have spin, but the particles don't actually spin. We say they have color, but they don't actually have color. And we say they have flavor, even though it's not actually a flavor. I think calling it a family would be better. Like, we have the electron family, the muon family, the tau family, species. Neutrino species would be a good word, but we call them flavors. Why? No idea. But then we can make funny jokes about buying vanilla ice cream and getting home and having chocolate ice cream. It would be fun if ice cream did that. Neutrinos do. Why do we call it flavor? Because physicists are terrible at giving things name, and they were like, hey, we need a property. Flavor's a property. Yeah, that's basically how we name things. There is no real reason to call it flavor. We just do. And it's confusing. It's like spin. Imagine something that is spinning, but it's not actually something and it's not spinning. That's how we define spin. Yeah, doesn't make sense. We just call it flavor because we do. Okay, let's go back to questions. So I mentioned that there are different things that can emit neutrinos. For an example, the sun, supernova, the early universe, nuclear reaction. So there's a question here by Prath of, can the human body spontaneously emit neutrinos? And I am actually not sure. I'm trying to think of the answer to this. Let's just do the typical thing and see if I can figure out the answer quite quickly. Do people emit neutrinos? So in order to produce neutrinos, you do need some type of nuclear reaction. And you have these nuclear reactions in pretty much everything. So humans do emit neutrinos, even bananas emit neutrinos. So you can actually produce neutrinos anytime you have any type of weak interaction, which happens in most nuclear reactions. Our cells do a lot of nuclear reactions when they burn energy, they burn stuff or they burn food to produce energy. These are all nuclear reactions. So yes, human bodies can emit neutrinos and do emit neutrinos, as do bananas. And this is fun because when you actually produce your neutrino detector, when you create your neutrino detectors, you need to isolate them from other things like people or other possible sources. So the places we put our neutrino detectors are in places that are really like isolated from everything. In fact, one of my favorite neutrino detectors is Ice Cube. And this is actually a good name for once. Now, Ice Cube is built 1.5 kilometers under the ice in Antarctica, and it is a detector that is 1 kilometer cubed. So it is 1 kilometer cubed of detector built 1.5 kilometers under the ice. And this detector is basically a string with balls attached, and each one of these balls can measure light. And this is 1.5 kilometers under the ice in Antarctica. And the idea of this detector is if a neutrino comes into the ice, has a weak interaction and produces something like an electron or anything that has charge, this charge going through this charged particle traveling through the water is going to produce a specific type of light, which we call Cherenkov radiation, which is what happens when you get high energy charged particle passing through something like water or something that has a specific density. Depending on the speed of the particle, you get this light. And this light is what we measure in Ice Cube. So Ice Cube is 1 kilometer cube detector built 1.5 kilometers under the ice in Antarctica. And it's just it's about 8,000 of these optical sensors, so 8,000 balls that were just lowered into pipes underneath the ice. And the reason it's in Antarctica underneath the ice is to isolate it from everything else, because there are so many things that can produce neutrinos. And you need a big surface area. You need something that is 1 kilometer cube, because it is very difficult to actually get enough of these reactions to measure things. You really need a neutrino coming at high enough energies to have a weak reaction, produce a particle that then produces the light that you can see. So there's a lot of steps involved in the process. And just a fun fact that Ice Cube is located in Antarctica, but it actually measures things that have come all the way through the Earth. The reason for this is because there's a lot of other things that can trigger reactions in a neutrino detector. So I'm going to drink some infusion now. So there are a lot of other reactions that can take place in the neutrino detector. So one of the ways of filtering out what is a neutrino from what isn't is by looking through the whole Earth, because a lot of particles, electrons, high energy muons, anything cosmic rays, a lot of these will already have different interactions within the Earth itself. But because neutrinos rarely interact, they can pass through the Earth practically undetected. So in Ice Cube, they actually have some sensors pointing kind of like down, so up to the night sky, sorry, and some pointing down through the Earth. And it's the ones going down that they're actually interested in, and all the ones that come from above, they remove because they're too close to be considered neutrinos. So they look for ones that have traveled all the way through the Earth. So this detector actually points kind of downwards or to the ground, which is very, very cool. Just some comments here. You thought bananas emit positrons, not neutrinos. Bananas do emit positrons and neutrinos. So potassium in bananas does undergo beta decay, as worse karma is saying here. I need a name to call you. I'm not going to call you worse karma. I believe in good karma, not in bad karma. Potassium, but as worse karma is saying here, there is this beta decay, which is this specific nuclear reaction that produces neutrinos, and it also produces positrons, which are anti-electrons. So bananas do produce both. Okay, so yes, humans do emit neutrinos. This is not a problem for our detectors because our detectors are really looking for neutrinos with specific energies. The higher the energy of the neutrino, the you measure, so you key your detectors to different energies. The energies of the neutrinos we're going to produce or a banana is going to produce are very, very, very low. And so they're not really going to be a problem for these detectors, but we still need to isolate these detectors from everything else. And this detector is called ice cube because it is one cube of detector underneath the ice. So it is actually a nicely named detector for once. Yeah, it's annoying to see accounts saying we don't build wonders anymore when we are busy building. Yeah, I know some people say that. It's ridiculous. Like the technology that we have today, the experiments we have today are just mind-blowingly amazing. You know, we are sending missions to space that are using lasers to look for ripples in space-time. How is that not amazing? This is just amazing. Is it understood how the neutrino masses vary? Is it considered an interesting research area? If not, excellent question. I realize I've skipped questions. I'll get to that in a sec. Going from the top, let's go through all of the questions. And then I'll carry on with neutrinos in cosmology, because for now I've just introduced neutrinos by themselves. Okay, where were we? We were up here. I could have dressed up as a neutrino. Yes, indeed. Okay, funny neutrino joke there. I do appreciate all the people saying that if I dress up as a neutrino at a conference, I wouldn't be able to interact. I'd be sprinting all the time. What did the neutrino say to the other conference goers? Don't mind me, I'm just passing through. Love the joke, Paul. Brilliant joke there. Okay, on to actual questions. Mito. In my work, I have observed the same phenomena. So talking about beta minus decay, we've observed the same phenomenon on the basis of which Pauli invented neutrinos. The energy spectrum of the electron is continuous because the anti-neutrino takes part of the energy. Yes. So it is very cool that you can kind of reproduce these experiments where people first came up with the idea of neutrinos. This is something you can reproduce in the lab, and it's very cool that, you know, this is something you can do. Okay, so there was a question from David Howden of how do we have maths? I think I answered that. It's because they change flavor or family or species. If they didn't change flavor, they would probably be massless. But the fact that we've been able to see them change mass means that that we've been able to see them change flavor means they have to have mass. So quantum physics thing, if you have any flavor oscillations, as they're called, you need to have mass. Also, fun fact, there have been 2 Nobel Prizes for the discovery of neutrino oscillations. I think the latest one was 2014, maybe, around then, at some point when I was doing my studies, which is a big range. Okay, question from Karma here. If neutrinos can oscillate, then how can we be sure decays always produce one particular type of neutrino? Example, tau decay produces tau neutrinos. What if it produces an electron? So then we get into something that I was going to avoid, but something that is called basically electron number conservation. So the number of leptons that go in has to be the same as the number of leptons that come out. And usually then you have some type of family conservation, so to speak. So if you have a tau involved in the interaction, you're always going to produce a tau neutrino. If you have an electron involved in the interaction, you're going to produce an electron neutrino. But then these can change. So how can we be sure that the interactions always produce one particular type of neutrinos? Just from everything we understand about how the particles fit together, if you have a tau involved in the weak interaction, you should be producing a tau neutrino, which then will change. And by the time it reaches us, it might not be that. Hope that answers the question. I'm doing quick fire questions now, so if anything is not clear, do ask follow-ups as always. Okay, another question here from David Howden. If the different types of neutrinos have different mass and mass is energy, where does the energy to change the mass come from when they oscillate? Love this question. So the energy needed to oscillate, they don't actually need energy to do the oscillating thing. And this is where things get interesting, right? Because the mass is kind of entangled with the flavor, but not in a direct way where you can say mass 1 corresponds to electron 1. So there's actually like 6 numbers that go around, like mass 1, mass 2, mass 3. The relation between these masses, like how much bigger is mass 2 regarding mass 1, and so on. And then the mixing angles. So the mixing angles basically tells you the chance of changing between an electron to a muon or a muon to tau. The change from electron to muon might be easier than from muon to tau, but it very much depends on how these are linked to the masses. So because they're not three like different things where you can say electron neutrino has this mass, tau neutrino has this mass, the energy needed to do this oscillation is kind of built into the way the neutrinos work. So you don't really need energy to do this oscillation, because oscillating doesn't mean changing mass. But the fact that they oscillate means they have to have non-zero mass. They have to have some mass in order for the oscillations to work, because the mass does play a role. Also the distance they travel. So a fun exercise we get to do as undergrads when studying this is like you produce an electron neutrino in the sun, calculate the chance of it being an electron neutrino by the time it reaches Earth, and you get a number of about 40% approximately, which is nice. It's just over 1/3, because it's easier to be an electron neutrino than to be the other neutrinos, just because of the way the numbers appear. But you can calculate that. It's a very fun thing to do. Okay. I'm going through the questions, which means I don't see the newer ones, then we'll jump to the newer ones and see if people have follow-ups. Do neutrinos have one speed in a vacuum, even if we don't know it, or can it have any speed at all, like normal matter can? So, because neutrinos are really, really light, they travel almost at the speed of light. The exact speed at which they're traveling will depend on the mass they're carrying. The reason that normal matter or that other matter can have any speed is because you can produce things with different speeds, but then you can also slow things down. Slowing down an electron is quite hard because it doesn't interact. So it's quite hard to slowing down neutrinos, not electrons. Slowing down neutrinos is quite hard because they don't interact. So if you produce a neutrino, it's going to have this kind of rest energy, this rest mass, which is going to make it travel at almost the speed of light. All neutrinos are going to travel at approximately the speed of light, but not quite at the speed of light. So other particles have different masses because you can slow them down. Sorry, different speeds because you can slow them down. It's quite hard to slow down neutrinos. Okay, let's see the questions. I see there's a lot of follow-up questions to what I was just saying there. So let's go through everything. I see, hey, Abyss, great to see you here. Have not seen Abyss here in a while. It's great to see you as always. Okay, more questions. Where were we? Question by Nadia here, which I really like. Is it understood how the neutrino's masses vary? Is it considered an interesting research area? It is. It is not well understood. It is a mystery. There's also the fun thing that we don't know why neutrinos have mass. So every other particle in the Standard Model gains its mass through talking to the Higgs boson. The Higgs boson is the one that gives everything else mass, even itself. But if we compare the masses of all of the particles, even we take the lightest non-neutrino particle, we look at the electron. This is like 0.5 MeV in some units. So we're just going to call it 0.5 MeV. So that's 0.5 mega electron volts. The neutrinos are going to have masses of around electron volts, so like 100 times lower. Why? Why do the neutrinos have masses so much lighter than all the other particles? What causes this? Where do neutrinos get their mass from? This is not well understood. This is something that is an open area of research, and there's a lot of different ways you can answer this question. There's a lot of different models, there's a lot of different hypotheses. We're not sure why neutrinos have mass. There's a lot we don't know about neutrinos. Now, I'm going to add another fun concept here, which is chirality. Chirality is about the direction that something faces. Some things have chirality, some don't. Like, if I get, let's say, this water bottle, this is kind of symmetric, right? Doesn't really have chirality. But if you look at your hands, there's a clearly defined left hand and right hand. And if you overlay them, they obviously don't overlay. You have to rotate one of them in order for them to line up. So my hands have chirality. They have left-handed and right-handed. Most particles in the Standard Model do not have chirality. Neutrinos do. All neutrinos are left-handed. All antineutrinos are right-handed. Why? We have no idea. But that is also a very cool thing. So at the particle physics level, the big open questions are, why do neutrinos have this chirality? Where do neutrinos get their mass from? And what is the overall mass of the different possible masses neutrinos can take? How do they change between one mass and the other? These are all open questions. And this is where you can approach it from a particle physics perspective, trying to answer these questions. There are a lot of experiments ongoing trying to answer these questions. I know some people pronounce it as chirality, and I pronounce it as chirality, but left-handed, right-handed. There's also, I will come back to that, great follow-up here by Pratt here directly underneath, because I mentioned antineutrinos, and there's a question here of, like, antineutrinos exist. I thought neutrinos are their own antiparticles like photons. That is also something we don't know. So particles can have an antiparticle. If you have an electron, you can have an anti-electron. Now, usually when we talk about when we talk about matter and antimatter, we're talking about changing the charge. So an electron has negative charge, a positron, which is an anti-electron, has positive charge. Neutrinos don't have charge, but we think they do have antiparticles. We have been able to see antineutrinos. This is something that you can also pull out in different reactions. So then there's the question of, is an electron neutrino and an anti-electron neutrino the same thing? This goes into the idea of this chirality thing, because all neutrinos are left-handed, all antineutrinos are right-handed. So could they actually be the same, just the two different chiralities of them? This is also an open question. So if you want the jargon for this, the question is, are neutrinos Majorana, which means they are their own antiparticle, or are they Dirac, which means they have a different antiparticle? They're different things. Some particles are their own antiparticle. We don't know if neutrinos are their own antiparticle or not. Another open question. There's a lot of open questions about neutrinos. 50 years of research to pin down most of the properties. Wow, yeah. 50 years of research. We're still trying to figure things out. Comment here from Karma. I think the flavor oscillation implies mass is a relativity thing. Basically, you want the particle to experience time to oscillate so it can't move at the speed of light. Yes, that is one way of thinking about it. Now, the problem here is that we are talking about particles, and putting particles together in the gravity map is quite hard, because we don't know how gravity behaves on the particle level scale. For this, we would actually need something like a theory of quantum gravity. See last week's episode where we talked about quantum gravity and how we don't know what quantum gravity is. But that is one way of thinking about it, about that in order to oscillate, you need them to experience time. But then you can ask the follow-up question of, do photons experience time? What does it mean for a particle to experience time? And then it gets quite complicated. Okay, question here by Scientisky. Do neutrinos orbit the center of mass of a galaxy? Very cool question. Now, usually when you're talking about something orbiting something else, this is a gravitational interaction. Neutrinos travel extremely quickly. They do feel gravitational interactions, but they travel extremely quickly. So if you produce a neutrino somewhere, it is traveling so quickly. It's kind of like the slingshot maneuver that they talk about in Armageddon. Or another way of thinking about it is like when some comets we see every 80 years, they come and go. Other comets just have a slingshot by us and then go off. They're moving too quickly to be caught up in our orbit. So it's the same for neutrinos. They are moving so quickly, they don't really get caught up orbiting another object. They just pass through. Because they are traveling almost at the speed of light, they're going to travel through and not really get caught up with things. Follow-up question from Abyss here. Is it theoretically possible that flavors of neutrinos have varying interactions with the Higgs field? It could be. We're not completely sure how neutrinos get their mass and why their mass is much smaller than all of the other particles. If you want the different families or the different flavors of neutrinos to interact differently with the Higgs boson, then you need some type of mechanism for this. And why would an electron neutrino interact or feel the Higgs field differently to a muon neutrino? This is something that is, again, an open question. And because there's not a clear thing of like electron neutrino has this mass, then it's quite hard to define what it means for the different flavors to interact with the Higgs boson differently. But it is an interesting conversation and an interesting thought to have there. Semi-off-topic question: what's the mass of a proton in terms of units of that table? So going back to the table here, the mass of a proton is 2 ups and 1 down. Proton is approximately 1 GeV. So A proton is made up of 2 ups, 1 down, yes, and it is approximately 1 GeV. It's not written here because you'd need to add them together, and it's not directly just adding the 3 together because then you have the energy, the binding energy of holding these together. It's approximately 1 GeV is an easy one to keep in mind, yeah. Okay. Need to get my cats to the groomer for, okay, good luck with the cats, groomer, hope that all goes well. It's not general relativity, but special relativity, no problem with quantum mechanics, yeah. So I agree. Special relativity, time dilation. Yeah, that is one way to think of neutrino oscillations, that you want them to experience time, therefore they cannot travel at the speed of light, and therefore they need to oscillate, or therefore they need to have mass. That is one way of thinking about it. Love the question here from David Howden. If neutrinos get their mass not from the Higgs field, could they have been around distorting space-time before the Higgs field switch on? Would that show in the CMB? Now, that is a great question, and I think I'm going to use that question to jump into the second half of what I wanted to talk about, which is neutrinos in cosmology. 46 minutes in, and we haven't yet got to the main topic today, which is neutrinos in cosmology. But I did take a 15-minute tangent at the start to talk about some random things. Your question, Abiz, was based on how leptons interact with the Higgs field. My assumption is that point particles have inertial mass, which neutrinos have. Yes, that does make sense. I'm not completely sure how we pull out the different interactions with the Higgs field, because we don't know how neutrinos interact with Higgs. Okay, so in the very early universe, after the end of inflation, we have a universe filled with particles. And at some point, these particles are going to annihilate. You're going to have photons and you're going to have positrons and electrons annihilating. You're going to have muons and antimuons annihilating. You're going to have neutrinos. So in the first few seconds of the universe, you can produce a huge amount of neutrinos, some other particles interacting, and just in general from the same mechanism that produces everything else. So in the very, very, very early universe, if we count just right after the end of inflation, you basically have 2 main things. You have photons and you have neutrinos. Photons are a bit more abundant than neutrinos, but these are the 2 main things you have in the early universe, photons and neutrinos. These behave as radiation. They're relativistic. They're traveling almost at the speed of light, or at the speed of light in the case of photons. Now, as the universe expands, we shift between a radiation-dominated epoch, where radiation is the dominant contribution, to a matter-dominated epoch. The reason for this is that radiation dilutes away faster than matter does in the universe. Yeah, you are not wrong, Prath. It has been 48 minutes with no CMB appearance. Don't worry, it is coming. It is going to happen. So radiation dilutes away faster than matter does in the universe, and matter dilutes away faster than dark energy. So as the universe expands, radiation is going to dilute quickly, and we're going to shift from a radiation-dominated time to a matter-dominated time later on, because matter is going to dilute away faster than dark energy, which doesn't dilute away with the expansion of the universe. We shift from a from a matter-dominated time to a dark energy-dominated time. So we go through these different stages of radiation-dominated, matter-dominated, dark energy-dominated. Now, photons, completely relativistic, always travel at the speed of light. They are going to be important during the radiation-dominated times, and today they account for a very, very, very small percentage of the energy budget of the universe. Neutrinos, on the other hand, are not massless. So in the very early universe, neutrinos are relativistic. They're behaving as radiation. They're speeding around. They're dominating the universe together with photons. But neutrinos do have mass, which means they don't dilute as quickly as photons do. And neutrinos actually do this transition, where at some point we can consider them to be radiation, and at some point we can consider them to be matter. This means that neutrinos are actually going to be important throughout a large part of the history of the universe, because they were important during the radiation-dominated epoch, because they are radiation, but they're also important during the matter-dominated epoch, because they're matter. So you have neutrinos behaving differently throughout the history of the universe, but still being there, still contributing. And this is really cool, because this means that neutrinos are going to have an impact throughout cosmic evolution. So I realized that I ordered my slides specifically for this, and they're not in the order I wanted them to be in. So Let me see if I can find my usual map of the universe, history of the universe. We have inflation, then we have this radiation-dominated time, then we switch to the matter-dominated time, and today we're in the dark energy-dominated time. I think this is much better in this one, actually, where we have the different developments. The neutrinos are going to be important in the early universe. They're going to be important today. So neutrinos will have an impact on the cosmic microwave background radiation. Neutrinos will have an impact on the large-scale structure of the universe. Neutrinos are going to impact everything in the universe. This is very cool because this means that we can actually use cosmology to study neutrinos. Because if neutrinos are behaving as radiation and then as matter, they're going to be there, they're going to affect different things in the universe. At this point, I want to answer a question that none of you asked, and I was expecting somebody to ask, but nobody asked it, but that's fine, I'm going to ask it anyway. I said that neutrinos don't interact with light, but they do interact with gravity, and they're practically zipping through you constantly unnoticed. They don't interact with anything else, and they behave as matter in the universe. So I'm talking about something that is matter that we cannot see, and that is everywhere in the universe. And some of you might be thinking, this sounds a lot like dark matter. It sounds a lot like dark matter, and you would not be wrong with that thought. In fact, there is a question of, should we actually consider neutrinos to be a part of the dark matter? However, neutrinos, we know how many neutrinos there are today, approximately, but neutrinos are not enough. There's not enough neutrinos to play the role of dark matter, this weird type of matter that doesn't interact electromagnetically. If all of the matter were made up, if all of the dark matter were made up of neutrinos, there wouldn't be galaxies today, because neutrinos are traveling too quickly. Neutrinos travel so quickly that they don't give time for structures to form. So if we think of the cosmic web, the web of galaxies that we have in the universe, in fact, we can use the very recent image from the Dark Energy Spectroscopic Instrument. This is actual data here. Every glowing dot here represents a galaxy in the night sky. And you can see we have this nice cosmic web structure where we have regions where we have a lot of density, regions where we have less density. We form this nice cosmic structure here. And this cosmic structure is basically governed by the gravitational force. If you have something like neutrinos passing by really, really quickly, they're going to wash out some of the structures. So you can actually simulate what this cosmic web here would look like with massive neutrinos and without massive neutrinos. And this is what you get. So what you can see here is this kind of cosmic web. This is a simulation of the cosmic web, where the brighter colors, the red, the yellow represents more density, the blue represents less density. And you can see we're kind of simulating this cosmic web here. On the left-hand side is what happens if you have normal neutrinos with mass. On the right-hand side, what would happen if we have neutrinos that don't have mass. And you can see that the amount of structures change. If you don't have massive neutrinos, neutrinos just pass by completely doing their own thing. The dark matter and the galaxies fall together really, really quickly. There's nothing dragging them around. There's nothing slowing them down. So you form these really big structures very quickly. You can see on the image on the right, you have a lot of very big things and not many small things. On the left, you have the opposite. You have matter more evenly spread out in the universe, which also means that if you have too many neutrinos, galaxies would look very different to how they do today. So neutrinos cannot be all of the dark matter, because if they were, galaxies would look vastly different. We wouldn't be here having this question. We can count neutrinos as a small part of the dark matter, but there are not enough neutrinos today to explain everything we've seen of dark matter, and neutrinos move too quickly to be all of dark matter. So if you want to count neutrinos as dark matter, they would be about 0.5% of the dark matter that we see today, which means we still need to explain all the rest of the dark matter. So most people usually don't consider neutrinos to be dark matter, because we still need to find all of the rest of the dark matter. So it doesn't really get as far. Is it possible that individual neutrinos are too fast to produce the effects of dark matter, but a galaxy-scale swarm of neutrinos is slow enough to do so? Then there is a question of, how would you slow down the neutrinos? Even if you have a swarm of neutrinos, because neutrinos barely interact, you're not going to be able to pile enough neutrinos together to produce enough effect to mimic all of the dark matter. Even if you put a big cluster of neutrinos, you're not going to be able to produce the same effects that we observe with dark matter. This washout effect of neutrinos is over 13 billion years or in a particular epoch. So this here is basically a simulation of the history of the universe. You start your simulation with the initial conditions and you see what happens. But here it is mainly focusing on massive particles, so you don't account for radiation here. But this is, you put everything we know in a box, you let it evolve for about 13 billion years, or we speed up the process. We don't have to wait that long, but you mimic that much evolution, and this is what you get. So this means that we can use galaxies to understand neutrinos. And I think this is very cool. Just going back to this image here. The one on the right has neutrinos with zero mass. When I talk about zero mass, what I mean is if you take all three of the possible masses, all of the neutrinos, and you sum together their mass, you can get a specific value. And this is the upper value, the upper limit we have on neutrino masses. The one on the right has zero neutrino mass. The one on the left has a neutrino mass of about 2 electron volts in total. So this is all three possible mass states of the neutrinos summed together. Neutrino mass of about 2 electron volts. This is an exaggeration. The one on the left has too much matter. If you compare the one on the left to what we actually see in the dark energy spectroscopic instrument, you can see that this one kind of lies in between these two here. It's kind of in between, especially if we look on the amount of structures that we have on small scales. It doesn't completely match either of these two. But this is exactly what we can do. We can use galaxies, we can use the distribution of galaxies to try to weigh neutrinos. And I think it's mind-blowing that we can take the overall distribution of galaxies in the night sky and use that to try to get the mass of the tiniest particle. The difference in scales here is incredible to me. And we're like, how do we measure neutrinos in cosmology? We take galaxies and we measure galaxies. Based on what galaxies look like, we figure out what neutrinos are doing. This is amazing. I think this is one of the coolest things that we can do. We have these tiny particles, they barely interact, they zip through everything, but they were produced in the early universe. Therefore, they affected galaxies, and therefore I can look at galaxies and measure neutrinos. Not just galaxies, though. Of course, if neutrinos play a role throughout the history of the universe, neutrinos are also going to have a huge impact on everything else we can observe in the universe. One of the biggest things is early, what we call Big Bang nucleosynthesis. So when we form the very first elements, when we form hydrogen and helium in the very early universe, there is a specific series of reactions that produce this. These reactions will also produce neutrinos. These neutrinos are what we call the cosmic neutrino background today. So this would be a background of neutrinos that broke away from everything else in the early universe. This cosmic neutrino background is a prediction of our standard model of cosmology. Based on what we've been able to measure of how many elements there are, how much hydrogen, how much helium there is, it matches exactly with what we'd expect if there is this cosmic neutrino background. And if the cosmic neutrino background sounds familiar, it is. It's because it's the older brother of the cosmic microwave background radiation, 59 minutes new backward. Cosmic microwave background radiation, the CMB, the oldest light in the universe. This is a map of what the universe looked like 380,000 years after the end of inflation. These are the photons that existed in the early universe in this radiation-dominated time, which later on broke away from everything else and have been traveling freely ever since. Because neutrinos are because neutrinos slightly heavier, they actually would have broken away earlier in the universe. Wait, let me rephrase that. Because neutrinos don't interact electromagnetically, sorry, what I just said there was wrong. Because neutrinos don't interact electromagnetically, they break away from other particles when the weak force stops being the dominant force. Photons break away later when the electromagnetic interactions freeze out. Neutrinos are frozen out by the weak interaction, so they freeze out within the first 3 minutes of the universe. So imagine if, apart from the cosmic microwave background radiation, we could get a map like this, but of neutrinos. Because there are neutrinos everywhere in the universe. If I hold up my thumb, hundreds of neutrinos pass through every second. These are the neutrinos that were produced in the very early universe. We know they should be there based on the primordial elements, or based on how much hydrogen, how much helium we have, we know they should be there. Also, in the very early universe, these neutrinos and these photons were talking to each other. So we can also use the cosmic microwave background radiation to measure neutrinos. So when it comes to neutrinos from cosmology, you really do have several different times at which you can do measurements. We can use primordial Big Bang nucleosynthesis to put one end. We can use galaxies today to get another end. You can use CMB, the cosmic microwave background radiation, somewhere in between. If neutrinos had more mass, this would look different. If neutrinos had less mass, this would look different. The way the blue and the orange blobs cluster together would change depending on the neutrino mass. So there are a lot of different ways we can measure the amount of neutrinos in the universe. This is mainly with Big Bang nucleosynthesis, so the primordial elements, and the cosmic microwave background radiation. And then you can use the cosmic microwave background radiation and galaxies to measure the mass of neutrinos. And this is still ridiculous to me that we use the universe to measure these tiny subatomic particles, just based on the fact that, well, these particles have existed throughout the history of the universe. So they affect the CMB, they affect galaxies, they affect everything in the universe. Let's use the universe to measure these particles that we can't measure otherwise. Amazing. Absolutely amazing. Okay, let's go back to the comments here. It's not about slowing down the neutrinos, it's about having lots and lots of neutrinos traveling in different directions such that their momentum cancels out, but their mass doesn't. Even if their momentum cancels out, but their mass doesn't, there still wouldn't be enough neutrinos. So based on everything I just said here, we can use Big Bang nucleosynthesis, we can use the CMB to get an idea of how many neutrinos there should be today. We know that today neutrinos only account for about 0.5% of the energy budget of the matter content, which means there wouldn't be enough neutrinos today to explain everything we give dark matter credit for. So it's not just about the speed of the neutrinos, it's also there's just not enough of them to be all of the dark matter. Is it possible for multiple sources, question from Ben here, is it possible for multiple sources of neutrinos to converge constructively or interfere? Wouldn't it have a higher density of neutrinos? Yes. So if we're talking about this cosmic neutrino background, you're also going to have sources on top. For example, supernovas or the sun or every star is also going to produce neutrinos. But we have the same when we do cosmic microwave background analysis. So these are the photons that are behind everything else. On top of this, you have the galaxy, you have other galaxies. You have to remove all of that to find this thing that's left behind. With neutrinos, it would be the same. If we could ever measure this cosmic neutrino background, we'd also have a lot of things in the way. We'd have neutrinos coming from the sun, we'd have neutrinos coming from supernova, we'd have neutrinos coming from different galaxies, and all of this is stuff we'd need to remove in order to get the cosmic neutrino background. So why am I not showing you the map of the cosmic neutrino background? Because neutrinos are just incredibly difficult to measure. We know how to measure photons, particles of light. You make them interact with electrons, you get a signal, you can measure it. Measuring neutrinos is much harder. The cosmic microwave background is at an average temperature of 2.7 degree Kelvin. Is that right? Yeah, about 2.7 degree Kelvin. At about minus 440 Fahrenheit, if you want it in that, minus 270 Celsius. The cosmic neutrino background is even colder. It's about half that temperature in Kelvin. So it's at about 2 Kelvin, which is, I have absolutely no idea in Fahrenheit, but 2 Kelvin should put it at about minus 271. Minus 269, around there. So it's a bit colder than the CMB. It's much, much, much harder to measure. Ideally, someday, I'll show you this map for the cosmic neutrino background, because that would give us a snapshot into what the universe looked like a few minutes after the end of inflation, not 380,000 years, just a few minutes. But that is extremely difficult to measure. But there are experiments set to measure this in the future. There are experiments with the mission trying to measure this cosmic neutrino background, which would be amazing if we got that. Yeah, nobody uses Fahrenheit for anything except weather, but I've realized that most of my audience are actually based in the US, so I try to give it in freedom units as well, because Fahrenheit makes no sense to anybody, but I know a lot of people think in Fahrenheit, so I try to give the temperatures in Fahrenheit as well if I know them. So cosmology can measure tiny, tiny, tiny particles by weighing galaxies. You take galaxies, you look at how galaxies look, and from there you say, haha, I know what neutrinos are doing, which is very cool. On doing this, we actually have the biggest constraints on the neutrino mass don't come from particle physics experiments, they come from cosmology experiments. Quite recently, we got the most constraining measurement of the sum of neutrino masses coming from the dark energy spectroscopic instrument. They've been able to put really tight upper bounds. Like if you add the 3 different types of neutrinos together, this is the upper bound on the sum of neutrino masses. However, there is a big caveat that this depends on some assumptions. You have to assume a cosmological model. Of course, we're going to assume lambda CDM, which is the standard model of cosmology and which gives us amazing predictive power of a lot of things that we observe. But if you change your cosmological model, you would change the cosmological constraints on the sum of neutrino mass. And why do I talk about constraints and not measurements? Because it's always easier to say, like, it can't be bigger than this or galaxies would look different. Now, the ideal case is that at some point cosmology will actually say, like, we figured out that the sum of neutrino masses needs to be this number. Can't be anything else, needs to be this number. And that is within reach. Within the next 10, 15 years, we're going to have enough data from Euclid, from the Dark Energy Spectroscopic Instrument, from next generation CMB missions. We are going to have enough data that we will actually be able to measure neutrinos from cosmology. So we should at some point be able to say, okay, cosmology says, galaxies say that neutrinos need to have this mass. And that would be very, very, very cool. But I mentioned that I'm at this neutrino conference where there's also particle physicists and astrophysicists, and there's all the conversations about, would this be enough if we measure it from cosmology? And the answer usually is no. We also need to measure it in particle physics experiments because they're very different ways of measuring, and there's different assumptions that go into it. So ideally, we would get the same result from both directions. One of my favorite questions to ask. We know from particle physics experiments that neutrinos must have mass. We know from the way galaxies look that at the time galaxies were forming, neutrinos had to have mass. But what happens if we keep pushing this lower and lower and lower, and we never measure the mass of neutrinos? What happens if we find that today in cosmology, neutrinos don't have mass? Are we talking about different neutrinos? Are particle physics neutrinos different to cosmology neutrinos? What would this mean? But however you spin it, it means new physics. It means something new and exciting and interesting. And this is why I love this question. So one of the questions at the conference that we're all asking a lot is, what happens if particle physics experiments and cosmology experiments give us different answers to the neutrino questions? That would be very, very fun. So when I did my PhD, I worked with one of the leading experts in neutrino cosmology. He's literally written a book called Neutrino Cosmology. And I learned a lot of neutrino physics during my PhD, and it was really, really fascinating. I only have 2 papers on neutrino physics. One of them is where we actually did a full analysis of, okay, let's take every possible future mission, space-based, ground-based, CMB mission, galaxy mission, let's put them all together and see when or how likely we are to measure the neutrino mass in cosmology. And our answer was, it's quite likely that we're going to measure the sum of neutrino masses within 10, 15 years. And that was a very cool thing. And that's the paper that has then led me to give this talk on Introduction to Neutrino Cosmology, which is a super cool topic. And I still think it's mind-blowingly amazing that we're trying to measure the mass of these tiny, tiny, tiny particles by looking at galaxies and the CMB. We take the oldest light in the universe, we take galaxies, and then we use that to try to measure the tiniest particles that are zipping through the universe. This is, this is the type of question that keeps me coming back to science. Cosmology just is so cool that we can do this, that we can look up there and go like, haha, I'm figuring things out. Lost track of why we can think, what if neutrinos might not have mass? Don't they have to have mass because they change flavor? Exactly, Paul, exactly. From particle physics experiments, from flavor changing experiments, we know that neutrinos have to have mass. But from particle physics experiments, based on what we know of the standard model, there are two there are two possible masses that we expect. So I didn't want to go into too much detail about this, but there's something known as the hierarchy of neutrino masses, which basically is the question of, do we have two light and one heavy neutrino, or do we have one light and two heavy neutrinos? So if you imagine this is a mass scale, do you have two down here and one up there, or do you have two and one? This is what we would call normal hierarchy, and this is what we would call inverted hierarchy. And depending on which one you want, you have minimum lower bounds from neutrino experiments. From particle physics experiments, the lower possible bound, the lowest number we can get in the normal case, in the normal hierarchy case, is 0.06 electron volts. So that is 0.06 electron volts. In the case of inverted hierarchy, the lowest number you can get, this is when you take all three types of masses possible and you add them together, the lowest you can possibly get from inverted hierarchy is 0.1 electron volts. The latest data from Cosmology for the dark energy spectroscopic instrument, so from the one that gave us this map last month, or actually 4 weeks ago now, is they cannot be bigger than 0.08. So that's 0.08. So particle physics is telling, let me actually just write that down again. Oh, I already have something there. Let's just write it down again here. In the case of normal hierarchy, we have 0.06, and this is a lower bound. In the case of inverted hierarchy, we have 0.1, and from cosmology, let me spell that right, cosmology, we have 0.08, has to be larger than, this has to be smaller than, sorry, larger here. So for a normal hierarchy, the sum of neutrino masses has to be larger than 0.06. In inverted hierarchy, it has to be larger than 0.1. From cosmology, it has to be smaller than 0.08, which means these two are no longer compatible. So from cosmology, it seems like we're pushing it lower and lower and lower. And this is the question of, okay, we're very close to saying inverted hierarchy doesn't work from the perspective of cosmology. What happens if we say that normal hierarchy doesn't work either? So we're not quite there yet, but it's fun to ask, like, what would happen hypothetically if particle physics tells us this is the minimum based on the fact that they change flavor, and cosmology says, well, I didn't measure that. I tried and I didn't find them there. They're not that big. That would be a problem, because you're cornering it from two different sides, and then you don't find it. So we're not there yet, but it's interesting to think, what if 10 years from now, neutrino says they have to be smaller than 0.01, and particle physics is saying it has to be larger than 0.06. You can't put these two together. Yeah, so there is we're not quite there yet, and also there's a lot of caveats about what we assume and what goes into it. But it's really exciting that we can study neutrinos from particle physics, from cosmology, and it's always fun to say, what if we don't get the same question? What if we don't get the same answer when we ask the question different ways? Comment from Abyss here: as if the Hubble tension isn't contentious enough, you want to throw particle versus cosmic neutrino meaning discrepancy. Yeah. And this is not just me. I can tell you that every time I've attended a neutrino conference, this question has come up. And it came up in the first week of the conference, and we've actually got a scheduled discussion about it in the second week of the conference, where the theme is, what happens if? And it's really fun, because what happens if means new physics, new theories, new ideas. And it's always fun to just have these ideas, like, okay, what if? Why not? Let's see what happens. So are we going to find a discrepancy? Probably not. I honestly don't think we will find a difference, but I think it would be really interesting if we did. If a neutrino is subject to quantum gravity, could its mass jump to a higher energy state in a weak gravitational field? I'm not sure how to answer that question. I think that's a very cool question. I'm not sure. I don't know enough about quantum gravity and neutrino masses to answer that. There's a question from John here, which I really, really like. Would gravitational lensing help measure neutrino speed? Yes, it absolutely does. And this is another way we can try to measure the sum of neutrino masses, and therefore the speed. They go hand in hand here, because gravitational lensing is a distortion of light due to massive objects. Neutrinos can actually add to gravitational lensing. So it's quite difficult, but you can also get bounds on neutrino mass using lensing experiments. We can slow down neutrinos enough to study them if only we used, if only we could use black holes. Well, black holes are even harder to study than neutrinos. But neutrinos are a very fun topic. Took me over an hour. I knew it would take me over an hour to get through this. And honestly, this is a topic that we could talk about for hours because there's so many angles, there's so many perspectives. We have a 2-week-long conference. Okay, it's like 2 days. It was Tuesday and Wednesday this week. It's Tuesday and Wednesday next week. It's 4 days of conference spread out over 2 weeks. It's really nice. And there's so much. There's so many talks. I'm learning so much at this conference, and I do every time I go to neutrino conferences. There are people working on so many different questions. The whole idea of the chirality, the mass, the antiparticles versus normal particles. And there are just so many open questions in neutrinos. But also, we know how to find the answers to these questions, and we're on it. We're working on it. And I think it's so nice to see a topic bringing together people from vastly different areas. Often I go to cosmology conferences and I bump into the same people, and that's fine. They're nice people, mostly. But at this conference, there's particle physicists, there's people in fields that I never expected to encounter in this type of conference. And we're having so many fun conversations. Also, a lot of the videos from this conference will be made public in a couple of weeks. Not all of them. It's up to the individual presenters. Mine will be made public, but just a warning that it is intended for people who work in neutrinos. So it's things are explained in a different way to how I explain them in this stream, but that will be available. And once it's available, I'll link the video. And as I mentioned, there should be an outreach event for the actual conference for neutrinos from home. I'm not yet sure when it's going to be. I'm not yet sure if I'm participating. I probably am. As soon as I have information, I will link it on my Mastodon. And yeah, so do follow my Mastodon. That is dchooper91_Cosmo. I'm on the astrodon.social server. And I will spread the information about the neutrinos from home outreach event as soon as we have it, because then you can ask even more questions, and then there will be a panel of experts on neutrino physics, which is always cool. You know, Dune, Super, Kamiokande, and Ice Cube are actively working on neutrino detections. Are there new ones? There are many new ones. I cannot remember the names of all of them. I think SNO is still ongoing, the Subdury Neutrino Observatory. There was a new one I heard about recently that has escaped me. There's there is Ptolemy, which is not ongoing, but is a planned one in the future, specifically to measure the neutrino background, the cosmic neutrino background. There's another one that is called something like Chime. Is it Chime? Something like that. I have the logo in mind of like two big towers, but I cannot remember the name of the experiment, and I should, because I know people who work in the experiment. There are many neutrino experiments ongoing. In fact, I think there's even a page on Wikipedia of like list of neutrino experiments, and there's a lot of them there. Do you get many non-professional physicists at these conferences? Not so many. Often space is limited at conferences, and you do have to register. Sometimes there is a selection process. If there's not enough space, then usually it's focused on people who work on the topic. Now, there are kind of like amateur scientists who come to some of these conferences, but it's often, the talks are usually done at a level where it's assumed that everyone there is an active scientist. So hobbyists are welcome at some of these conferences, but it's not common for them to be there. And usually there are, especially towards giving talks, there are criteria, and there's just not enough space for everyone to give talks. So usually there are harsher criteria towards giving talks and presentations. But especially these remote conferences that then put all of the material online, I think it's really nice, because then anyone can go and watch them. I tick the box of, yes, put my video online once it's done, because why not? Exactly, it can go out there. Okay. Now in 20 minutes today, it's longer than expected, but I hope I convince you that neutrinos are really cool, and neutrino cosmology is amazing. And the fact that we can measure these tiny particles with galaxies is something I will never stop being amazed by. The fact that we can use the cosmic microwave background radiation, the first elements that appear, to measure these tiny particles is absolutely amazing. And I hope I convince you of that as well. Okay, some brief couple of cosmology news. You already mentioned that I have a couple of topics planned for the next few weeks, for the next few streams. One of them is waiting, some paper coming out. Then there's one I want to do on ups and downs of academia at some point. I am happy to announce that very soon I am actually going to have someone from the Dark Energy Spectroscopic Instrument join on Cup of Cosmology. He's someone who some of you might recognize from the Aachen days, and he's agreed to come as one of the DISY members. And he's going to be on Cup of Cosmology soon. We just need to figure out a date, but that's going to happen. And I'm super excited to actually have an insider to come and talk about Dark Energy Spectroscopic Instrument. I did a stream when the results first came out, but it will be really nice to hear the perspective of somebody who was actually involved in getting this and has spent many years working on DISY stuff. So looking forward to that one. Also, you don't mind this length of live stream even longer? Yeah, I know you all don't mind. I do, because kind of after an hour, I feel like my voice is breaking and I'm like, I'm tired. So if your regular videos were speed of light, today's video was the speed of neutrino. Yeah, it was, yeah, there was a bit of time dilation happening, a lot to cover, random tangents about cowboys at the beginning, which is always a fun tangent. I'm just in a good mood today, so my brain is all over the place. Good reasons, good stuff happening. Yeah, so I have a couple of topics planned. I'm also thinking of ways of expanding Cup of Cosmology. I'm thinking of new directions to take the show. No major changes. You know, the weekly live stream is still going to be there. I'm thinking of adding things, not taking things away. This will come soon. And I know some of you last week mentioned that it would be good to have kind of a database of what I've covered in each stream. I'm looking into that. I have some ideas, and that made me open the spreadsheet where I technically keep track of all my streams and realize that I have not updated that in 16 months now. Last update was January last year. So I have a lot of backlogging to do. Fortunately, I do somewhere have record of everything. Cup of Cosmology, TikTok, let's go. You are not completely wrong. Now, not necessarily TikTok, because I don't like TikTok and it has been banned in the US where most of my viewers are based. However, Cup of Cosmology Shorts, Cup of Cosmology Instagram. Not saying it's going to happen yet, no promises, but stay tuned. Exciting stuff coming as soon as I get round to it. A very vague announcement there. So yes, you can expect more content going forward. I'm going to look at more avenues for Cup of Cosmology. I have ideas. Stuff is happening. And there will at some point be, I'll make the videos more searchable so that you can actually find out what I talk about in these random AMAs. Today there's a clearly defined topic, neutrinos, but some of them are just like, ask me anything. And then we talk about quantum gravity for 45 minutes. So I am going to find a way to like classify this so that it's a bit more searchable and a bit more usable for everybody. Main takeaway here is that cosmology is very, very cool, and I'm going to do a lot more stuff with Cup of Cosmology in the future because it's just so cool. Barcelona to Stockholm is a long way by train. It is. I have done it. It is really, really fun. It is highly recommended routes, but it is very, very fun. Wheels of Cosmology, haha. Egg Cup of Cosmology. I like that you were trying to figure out a name because honestly, same. I was like, espresso of cosmology doesn't rhyme. Doesn't have the Cup of Cosmology alliteration that's there. Alliteration. Anyway, stay tuned. So, Cup of Cosmology should be back next Sunday, hopefully. I'm going to have another busy week, but I think my next 3 months are busy. But I'm going to have another very busy week. But I don't think I have anything planned next Sunday. No costume parties happening to my knowledge. At least none that I want to attend. So, Cup of Cosmology should be online next Sunday, same time as always. If you want to figure out when that is, there is a time zone converter on cupofcosmology.com. So you can go to cupofcosmology.com, figure out when the next stream is going to be in your own time zone. But Cup of Cosmology should be back online next week, same time as always. I hope to see you all again then. And I hope in the meantime, you'll stay safe and take care of each other.